So now I've got all of these, right? So now I've got them finished, and I need to just use the ones that I've got. I can't add any more dots. I can't add any extra hydrogens, carbons, or nitrogens because I've already got them all down. So this is the point where you know you got to form a multiple bond. So I know I can't form multiple bonds with hydrogen because hydrogen only ever ends up with one bond. So the only option is to form a multiple bond between what? Yeah, between carbon and nitrogen. So carbon and nitrogen are the only ones that can end up having multiple bonds. So now I go in and I'm going to just move. I'm going to move this nitrogen dot. Oh, it's not going to let me move that one. I'm going to take that one away and move it over here. I'm going to move the carbon, which is black. I'm going to take this one away and move it over here. And then I'm going to do the same thing, but I'm going to do it with these ones on the top. They won't let me erase them. Move this one into the middle and move this one into the middle. Okay, so the ones that I scratched out, they should be gone. I just can't erase them unless I close this too. So this leaves me with a nitrogen with 3 dots, 2 up here. There's its 5, and it's connected to a carbon. The carbon has 3 of its electrons shared with the nitrogen, and the last electron is the one that is shared with the hydrogen. So when I have those 3 pairs of dots, when I transfer this to a Lewis structure, I would have a triple bond. Okay? So I'd have H dash C, then dash 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 with an N. And it doesn't matter where those non-bonding electrons of nitrogen, you could put them above the nitrogen, to the right of the nitrogen, below the nitrogen. As long as they're connected to the nitrogen, that's fine. It's hydrogen cyanide. Okay? Honestly, these are the ones to practice. These are the ones, if I ask you to draw any on an exam, these are going to be the ones that I'm going to ask you to draw. I'm not going to give you like great big huge ones. We'll wait till next chapter for those. But for just the simple ones, it will be these ones. So we talked about naming ionic. So remember that when just generally naming ionic molecules, remember you use the whole name of the metal, first part of the nonmetal, and then you add IDE. Unless it's a transition, you got to use the Roman numerals. Unless it's a polyatomic, in which case you got to use that. Right? But sort of the first part of the nonmetal plus IDE. So that's kind of like the basic plan with ionic. Covalent's a little different if you're talking about what they call binary compounds. Binary just means 2. So they found, hey, we have H2O. That's a covalent molecule because it's nothing but hydrogens and nonmetals. But wait, you can also have this. Wait, how do you name that? Okay, so if the first one is a hydrogen with 2 oxygens, but because we're talking about sharing electrons, we can also have a molecule that has 2 hydrogens and 2 oxygens. You can't have that with ionic. With ionic, NaCl, that's the only way it combines. One sodium and 1 chlorine, so the formula would only be NaCl, so the name is just sodium chloride. But here, water, H2O2, could be like this, right? So you've drawn that one, so you remember that one. But I could actually have an oxygen linked to another oxygen, linked to a hydrogen, linked to a hydrogen. So can you see how that could happen? Because oxygen has the ability to have 2 covalent bonds. Do you see each oxygen has 2? Hydrogen has a single. So can you see how those can exist? Because we're sharing, not transferring. So we can get much more complicated in our arrangements and structures with covalent than we can with ionic. So they said, okay, because of that, you have to indicate the number of each element in the formula by using number prefixes. So the number prefixes are these. You won't see these very often, but I will tell you through 10. Okay, so 1, they always use the term mono. 2, di. 3, tri. Those ones aren't too bad, okay? But 4 is tetra, okay? Instead of quad, it's tetra. And the way that I remembered this when I learned this is because, do you remember the game Tetris? Do you remember the little game where the blocks dropped? And it was either a little square of 4 or 4 blocks in a row or 3 and then a turn like an L. So that's where the name came from, because tetra means 4. So they were just ways of arranging blocks of 4. So tetra means 4. But then from there, do you see those look like geometric shapes? Like a pentagon is 5-sided. A hexagon is 6-sided. Heptagon is 7. Octagon is 8. Nona is 9. Deca would be 10. So from here forward, it's really just geometrical shapes. They really match. So you've really kind of got to learn to remember 1 is mono, 2 is di, 3 is tri. Most people remember those okay. But then that 4 one is kind of strange. It's a tetra. So now, whole name of the first element, first part of the second element plus IDE. So do you see the part I wrote in red at the top? Do you see how that sounds just like ionic? Sodium chloride. Whole name of the first element, first part of the second element plus IDE. So that part's exactly the same. But I've got to use a number prefix to indicate the number of the first element and a number prefix to indicate the number of the second element. The only exception, I do not have to use mono if the first element is a 1. If the second element is a 1, then I do have to use it. So if I have NO, what would I call this? So N, whole name of the first element, so that is nitrogen. I do not have to put mono because it's 1, but I do for the oxygen, so that would be what? Yep, so when it's monoxide, you shrink the O's, like you only use 1 O, so you call it monoxide. So what's the second? What's N2O? If there's 2 nitrogens, then I have to use di. Still use the whole name of nitrogen because it's the first element, so dinitrogen. And since there's only 1 O, I would still use, yep, it's a monoxide. Dinitrogen monoxide. Crazy? Okay, what is then NO2? What is N? Nitrogen. And then O2 would be, yeah, dioxide. What if I had N2O4? 2 N's. Always use the full name of the first element. Then, what's 4? So when you have a vowels come together like mono-oxide, you drop the O of mono. Same thing here. If you have the 2 vowels like tetraoxide, you would just drop the A and it'd be tetroxide. I won't mark it wrong if you forget to drop it. I don't really care that much. But if you're answering questions in your homework, if you have 2 vowels, then they get dropped. The prefix number vowel gets dropped off. So like if you had pent and oxide, it would be pentoxide, no A. If you had oct and oxide, it would be just octoxide. Sounds really strange, but all right. So by this, what is CO2? It's one that's pretty familiar to everybody, but that's why they call this, yep, carbon dioxide. So carbon dioxide means 1 carbon, 2 oxygens. So if the first element only has a 1, you don't have to use mono. So now by this, what is H2O? It's water. But what's its fancy name? Dihydrogen. So that would be dihydrogen because I have 2, H2, monoxide. That tells me 2 hydrogens, 1 oxygen. Notice none of these have metals. These are all non-metals in hydrogen. So we'll practice a couple of them. So we got CO2 already, right? So CO2 is carbon dioxide. And you can have carbon monoxide, carbon dioxide. You can even have carbon trioxide. And this is the reason, because there's different numbers of them, this is the reason you have to use number prefixes. So what's CBr4? Carbon. What is 4? Tetra. And then first part of the second element plus IDE, so that would be bromide. Carbon tetrabromide. So N2O4. Dinitrogen. It's hard to say it this way. Like you have to kind of get used to just seeing it this, but dinitrogen just means 2 nitrogens. And you always say that if it's out front. And then, tetroxide. So if you use oxide, you drop that vowel if there's one in it. So NH3, this is ammonia, but NH3 would be called what? N is? Nitrogen. Tri. So it's not hydroxide because remember that's the OH. But so you use the first part of hydrogen plus IDE. So what do you think it sounds like? It's hydride. So that's nitrogen trihydride. Now hydrogen you haven't used in an ionic naming. So that's why it sounds very strange. Because remember we've done bromide, fluoride, iodide when we were doing the ionic, because it's a metal and a nonmetal. So you've kind of seen the oxide, bromide stuff, but you really haven't seen hydrogen as a second element. So that's the one, that's why people are like, I don't know, I've never heard it. And it's just because we haven't really used it. So if you see the hydrogen second, it's hydride, okay? But remember, like with this one, hydrogen's out front, so you don't use hydride, you just call it what? What's H2O2? Its common name is peroxide. That's hydrogen peroxide. But you would call it by its fancy name, it's dihydrogen, because you always use the whole name of the first element. And then O2 would be dihydrogen dioxide. So the last one, NF3. 3 is? Nope, F. What's F? Fluoride. Yep, so trifluoride. I don't know, but for some reason people still want to think that fluorine is FL, which is Florida. It's not. Actually, there is no element with FL. That's a state abbreviation. So I see that all the time. So it's just fluoride. And remember, it's UOR, like not OUR, because that's flour. Those are like 2 common misspellings and then common abbreviation oddities that I see. I'm like, why would they do that? All right, now it's gone again. God bless you. Okay. So now we can actually tell the difference. We can tell them apart. We can tell, well, which one's ionic and which is covalent, and how do you name them? So if you're given an element formula, or if you're given a compound formula, or if you're given a compound name, you can identify if it's ionic or covalent, and you can identify what its name is or get the formula from the name. So here's like the little flow sheet, the flow sheet. So we're going to practice. So 1, I need to know, is it ionic or covalent? Okay, and the trick is look at the first element. So whether you have a name or if you have a name or you have a formula, it doesn't matter. Look at the first element in the name or the formula. If the first element is a metal, then you know that you have ionic. Okay? So you always have your periodic table, so you don't have to memorize what things are. But how do you tell a metal from a non-metal? You look at the zigzag line, right? So you just look at the zigzag line. If the first element is on the left, I know it's ionic because those are all metals, except hydrogen. It really belongs over here, okay? If the first element is a non-metal or hydrogen, then I know it's covalent. So if it's non-metal and hydrogens included in this, then I know it's covalent. Okay, so if it's ionic, and it includes iron, chromium, or copper. If there's iron, chromium, or copper, then I know I have to use number prefixes. I know then I have to use the Roman numeral, right? So I'm going to end up with like iron with the +2, or I have iron with the +3, because those can have a different number. So I know in doing the naming, I'm going to have to put that Roman numeral between the metal and the non-metal. If not, if it's group 1, 2, or 3, so if it's like lithium, sodium, potassium, beryllium, magnesium, calcium, or aluminum, because that's the only one really in group 3. So if it's the first 2 columns or aluminum, then I know I just name it. No Greek prefixes, no Roman numeral. It's just like sodium chloride. So I just use the whole name of the metal, first part of the non-metal, plus IDE. Right? So we can have things like Al2O3. We can have things like NaCl. Whereas up here, we can have FeCl2. We could have FeCl3. That you would have to be able to tell the difference between them. If it's all nonmetals, then I know it's covalent. Nonmetals and hydrogen, then I know it's covalent. And here, I always use the number prefix. So if you have something like NO2, CH4, I'm thinking like H2O. So anything like that, then I know that those are covalent because there's no metal. Only nonmetals and hydrogen. So that's really the trick. The trick is look at the first element. So we're going to do these ones. You tell me first, is it ionic or covalent, and then tell me the name. So C2H4, is this ionic or covalent? How do you know? Okay, where's the metal? So what's the first one? So C2 is? So C2 is carbon, hydrogen is H. Remember, so if it's nonmetals and hydrogen, then I know that that's covalent. Right? So this is a nonmetal. It's really the trick. Just look at the first element. So the first element's carbon, so on to the right of the zigzag line. That's how I know it's covalent. What about the second one? Right? Because this is a metal. This is a metal, so I know it's ionic. What about the next one? Nitrogen. Where's nitrogen? That's a nonmetal. So I know that that's covalent. What about CaO? Right? Because this is a metal. CO? Covalent. Right? Carbon is a nonmetal, so I know it's covalent. PO3? Covalent. CCl4? Because carbon, again, nonmetal. S2O6? Covalent. I was just trying not to trick you into getting every other. And then the last one, NABR. Ionic, because see, this one's a metal. That's ionic. So you can see that's really the simplest way. Just go along. Doesn't matter if I gave you the name or the formula. Just look at the first word Or look at the first element in the formula. If it's a metal, it's ionic. If it's a non-metal, it's covalent. Okay? And 99.9% of the time you're right, unless you have ammonium. That's the only time that doesn't work. Okay? So if it's covalent, do I use number prefixes or no? Does covalent, does C2H4, do I need number prefixes? Yeah. Yes. If it's covalent, I have to use what I call the number prefixes. So I have to use mono, di, tri, tetra if it's covalent. So that means C2H4 is dicarbon tetrahydride. Right? So you take hydro from hydrogen and add IDE. You have to use those Greek number prefixes if it's covalent. So let's go down and do this one. So what's this one? N2O2. Dinitrogen and dioxide. Yep, dinitrogen dioxide. So then go down here. Let's do this one, CO. It's not cobalt, it's capital C, capital O, so I know that that is carbon and oxygen, so that is, yep. Go back. No. Okay, nope. Last two, computer. Okay, there's carbon. Oh, it just went away. That is carbon monoxide. Right? One oxygen, one carbon, I don't have to put mono, but since the second one is only one, I have to have mono there. So CO is carbon monoxide. You've probably heard of that. So PO3, it's also covalent. So that is, what's P? Phosphorus. So phosphorus. And then what? Yep. And you keep the tri, you don't drop the I. I don't make the rules. But CCl4. Yep. 4 Cls would be tetrachloride. Yep. Carbon tetrachloride used to be used as like a fire extinguisher. Because it's really heavy and it would like smother a fire. But when it gets hot, it breaks down and makes chlorine gas. So they found that that wasn't so great for people. So they don't use it anymore. But that's like one of the first uses there. Because it's super heavy. So they would just drop it on a fire and it would like take all the oxygen away from the fire and it would go out. All right, what about this last one? So here's the last covalent one. Then we're going to go back and do the ionic. So S2O6. S2. Disulfur, right? You use a whole name, even though that sounds strange. Disulfur, and then, what is 6? Hex oxide. Disulfur, 2 sulfurs, hex oxide. Okay, so now let's go back and do the ionic. So K3N. Yep, potassium. Potassium what? Nitride. Super easy. No number prefixes, remember? So it's just like sodium chloride. You don't have to use number prefixes. That's the only way potassium and nitrogen will combine, because they transfer electrons. So then what is CaO? Yep, calcium oxide. And then the last one, NaBr. Sodium bromide. Nope, because it's ionic. So just put yourself a note. If it's ionic, no number prefixes. So potassium nitride, no number prefixes. Calcium oxide, just whole name of the metal, first part of the nonmetal plus IDE. That's all you have to do. So I gave you this, right? So remember, you did this front page, right? Didn't you guys do all the ones on the front? Yeah. Okay, so now the back. So the back page, let's see, the back page. What did you do? So I know I saved that. Okay, so again, so if you missed any of these ones, if you want to go back and like practice them again, I do have this posted. This is actually posted in Moodle. So it's just listed as the practice sheet. And so we went through and did all of these. So Amber, like, you can go back and practice this one. The answer sheet is posted in Moodle. So down here, so you tell me, what is the rule for naming ionic compounds? You use what? Yep, okay. So in this, whole name of the metal plus then what? Plus IDE, like sodium chloride, right? Whole name of the metal, first part of the nonmetal plus the IDE. So example, Mg3N2, what would I call it? Yep, magnesium nitride. No number prefixes needed. That is the way that they combine. If I want to go from the name to the formula, like calcium iodide, what do? Like do this in like the two-step thing. So what do I write first? Calcium iodide, what would I put? Yeah. C, A. And what would its charge be? +2. How do you know? It's the group number, right? So remember the metal, it's the group number. So that's the group number. And then iodide, what's that? What's its symbol? I. And then what's its charge? -1. And how did you know? Right. So I figured out that charge because it's 8 minus its group number. So you list the symbols, assign the charges based on those rules. Now what do? Then you do the swap. So what this is going to tell you then, so the charge on the calcium tells you how many iodine. The charge on the iodine tells you how many calcium. So that's what I mean by the swap. And that's how you figure out the formula. So the final formula ends up being what? I2. Right? If there's only one, I don't have to add a 1 like calcium because the -1 of the iodine tells me 1 calcium. So when I do the swap, it's just CaI2. Okay, so to do the opposite, so you write the symbols, assign the charge to each, to the metal and the nonmetal, do the swap. Charge on the metal tells you how many nonmetals, the charge on the nonmetals tells you how many metals, and then if you can, simplify. And do you remember what I mean by that? So when I say, if they came out and it was like Ca2O2, if they were both even numbers, simplify it to CaO. Okay? It doesn't happen very much, but if you did yours and you notice, oh, they're both 2s or they're both 3s, you could simplify that. All right, so now the rules for naming covalent compounds. So unlike the ionic, what would you say? You're going to use okay, so I have to use number prefixes. Except yes. So if element 1, well, better way of saying it, first, then you have no mono. I have to use a number prefix. What else? So how am I going to name this? Like N2O4. What do I use for N? Okay. So by that, I know that I have to use the whole name of the first element. Then another number prefix. And do I use the whole name? Then I'm going to use what? So O4 is what? So I use first part of the second element plus IDE. Dinitrogen tetroxide. So what is phosphorus trifluoride? How would I write the formula? What's phosphorus? And since there's nothing in front, then I know there's only one. So then trifluoride would be yep. So that would be PF3, phosphorus trifluoride. If the first element's a 1, you don't have to put mono. Okay, so here's the last one. So in this, I'll give you a couple minutes. Okay, so in this, from the formula, tell me the name and tell me if it's ionic or covalent. It might actually be easier if you just go through and identify ionic versus covalent first. Then, from the name, give me the formula. From the formula, give me the name. This one throws in some polyatomics too. And a transition metal. So here's this one. So in the first one, so if you look at the name and you see the first word is iron, is that a metal or a non-metal? It's a metal, so that means this is ionic. Right? So this is a metal. That's how I know it's ionic. So if I look at Ca parentheses NO3 2, what is calcium? It is a metal, so I know that this is ionic. Okay, if I look at S4O2, what is S? It's a nonmetal, so I know this is covalent. Potassium nitride. Potassium is a metal, so that means this is ionic. PBr3. P is, so that means it's a nonmetal, so this is a covalent. Pentanitrogen. Nitrogen is a nonmetal, so that means this is a covalent, right? Hopefully everybody's gotten those. So Cu3P. Cu is a metal, so this is ionic. And the last one, ammonium. So what do you know about ammonium? It's tricky because ammonium is a what? Anybody remember? It's a polyatomic ion. So what is that? It's going to be what kind of a bond? It's got to be ionic. So this is a polyatomic. And because of that, I know this is ionic. So polyatomic ions always form ionic compounds because they exist as ions. Okay, so now, change color. Let's go to the blue. So now in this, when you go to do the formula from the name or name from the formula, name to formula, you take iron, and it's iron 3. What does iron 3 tell you? That it's a +3. Sulfide is sulfur, so that is in group 6, so it's a -2. So now I know, I wrote my elements, I assigned the charge, now just swap them. So that means that now I have Fe2S3. Done. Okay, so what about the next one? The next one's ionic. I got to just go from the name to the formula. This one's pretty straightforward. What is that? Calcium nitrate. Calcium, whole name of the metal. Now when you have, I put down there, if you have a polyatomic, you just use the name of the polyatomic. So remember there are 7 of them. I gave you a list of 7. I'm sure you're going to want to put those on your note card, right? So you want to remember like NO3 has a negative charge and it's called the nitrate. So this is calcium nitrate. So S4O2, what would its name be? S4 tetra. Tetra, sulfur, and what else? Dioxide, yep. So if I have something that's ionic and it's potassium nitride, to figure out the formula, I have to put down the symbols. Potassium is a K. Come on, stop doing that. Potassium is K, and its charge +1. Nitrogen is an N, and the charge is -3. So remember, the metal, it's its group number. The nonmetal, it's 8 minus its group number. Now I just do what? Swap them. If it's ionic, I now just swap them. So now that's K3N. PBr3 is covalent. So what's its name? Phosphorus. Yep, tribromide. Pentanitrogen trihydride. Sounds super crazy, but pentanitrogen means how many nitrogens? 5. So this is N5. And then trihydride means 3 H's. H3. C3P, ionic. So in this name, there's one thing I have to do that's kind of weird and special. Because it's copper, what do I have to include? The Roman numeral. So that means that I've got to figure out what the charge on the copper is. So if I have Cu and a 3 in the P. So what's the charge on phosphorus? -3, right? Because it's in group 5, so 8 minus 5 tells me it's a -3. Do you see those are the same? See that the copper is a 3 and the phosphorus is a -3? So that means if I have 1 phosphorus, what's the charge on my copper? It's 1 and 1, so that will be a +1. Does everybody remember? So this, it's like doing the reverse swap. So see, if the number on the copper matches the charge on the nonmetal, then I know that the other two are going to match as well. So in that one, that means that this is copper what? Copper 1 phosphide. Okay, and then the last one. So the last one's ammonium phosphate. So you got to look at the polyatomics. Ammonium is what? It's NH4 and has what charge? Ammonium. It's one of the 7 is the ammonium. It's the only positively charged polyatomic, right? So it's NH4 what? Plus. So it's got a plus. And then phosphate. What's the phosphate? So phosphate is PO4 with the -3. Okay? So now I've got those. How do I swap these? What do I have to make sure I include? The parentheses. So see that the ammonium is a +1. The phosphate's a -3. So they're not the same. So when I swap them, which one gets parentheses? The NH4 does. So I'm going to have to go parentheses, NH4, 3, and then PO4. I don't have to put parentheses because it's only a 1. Okay, did anybody get all those right? Okay, well, these are good ones to kind of practice. Like, these are good examples of ones to practice. Picking out ionic versus covalent, naming ionic, naming covalent, and then just going back over those transition and polyatomic ones. I will save this and post it. So this will be the answer key will be posted in Moodle. So if you go back and look at this one, you can do some more practicing them, just reviewing. So I'm just going to hold that. Okay. So shape of these covalent molecules. So we've talked about like the putting together covalent molecules like CH4. We've talked about naming molecules like CH4, it'd be carbon tetrahydride. But these are not flat structures. And when you draw them on a piece of paper, you always make them look super flat. But in fact, remember that these are 2 electrons. Every line that you see in a covalent molecule is 2 electrons. And you know electrons are negatively charged. So I tell people like, so these 2 electrons, they're shared, which means that they just do this. They just go back and forth, back and forth. They go from the carbon to the hydrogen, carbon to the hydrogen. They're in constant motion. So they end up spending some time with the hydrogen, some time with the carbon. But those are negatively charged, but so are the other pairs of electrons. So what they found is, they found that these valence shell electrons that are part of the bonds, they repel each other. So they have this repelling force, and that creates a 3-dimensional shape. So there's lots of interest in trying to figure out, well, we can draw like a 3-dimensional structure using the wedge and the dash. So when you see it looking like a wedge, that is supposed to simulate sticking forward. The dash should really simulate going back. So like if you were looking at this on the board, so in CH4, this carbon and these hydrogens would literally be like flat on the board. But this would be like the hydrogen sticking forward. So that's what they use for the wedge. This would show like the hydrogen sticking back behind the board. So they try to do that to try and show this fact that it's more 3-dimensional. It's not just a straight up, one down, one left, one right kind of thing. So then came the question of, okay, well, how do we actually show this? So they came up with what they call the ABN. Okay, so the ABN designation, or this is just a way of describing a shape that an atom can have. So A is always the atom you put down first when you draw them. So they're called the central atom. The central atom is always the atom that needed the most bonds. So remember when we were drawing like CH4, H2O, NH3? The central atom is always the one in the middle. B is the number of bonded groups. And so what I mean by that is if you're looking at CH4, so can you see that with CH4, I have 4 bonded groups? Carbon with 4 connected to 4 different things. But under these conditions, do you see that this is 2 bonded groups? So I have carbon attached to 2 oxygens. It's 4 bonds, but they are only 2 groups it's connected to. So this, even if I had this, that would still just be 2 bonded groups. Just like this has 4. So that's what the B stands for. Now the N stands for what they call the non-bonding electrons. So remember we were talking about those, and I was like, make sure you put in those non-bonding electrons. Those are the ones that aren't between 2 atoms. Those are the ones that belong to an atom itself. Like remember oxygen. So oxygen has, like if I have water, like this, oxygen has 2 non-bonding electron pairs. So those are the N. Same thing here, if I had nitrogen, it would have 1 pair of non-bonding electrons. So this would be 1 N. This one would actually have 2 non-bonding groups. And there are actually electron pairs. So it's always by pairs, not by singles. But what do you think about carbon? Does carbon have non-bonding electrons? Does it have dots that belong just to it? No. Right? All of its electrons participate in bonds. So carbon never has non-bonding electrons. That's like 100% of the time, not 99.9% of the time. Well, for us. In other chemistry classes, they might have them, but not in us. Carbon never has an N value because all of its electrons participate in bonding. Okay, so non-bonding pairs, though, they're actually important because non-bonding pairs actually take up more space than bonding pairs. So if we look back at that water, H2O, like this, right? So we have oxygen with its 2 sets of non-bonding pairs. Those electrons hang out with the oxygen exclusively. The ones with the dashes, those electrons go back and forth. So can you see these electrons go over here, come back, go forth, and keep going back and forth. But these actually stay only around oxygen. So they actually take up more room. The 2 electrons that are non-bonding take up more room than bonding electrons. So they have kind of like their space. And they actually push bonding electrons and have a repelling effect on where bonding electrons are going to be. So this affects the shape, because if you didn't have those, do you see that oxygen, if it didn't have non-bonding electrons, the electrons would want to get as far apart as possible and they'd be on opposite sides. But because of the non-bonding electrons, they get shoved and they can't get far apart. They end up getting pushed together to some degree. So this kind of shows how nitrogen and oxygen do this. So if you look at the nitrogen, here's its non-bonding electrons. So those 2 electrons take up that space, and they like kind of push the hydrogens further down, so they can't just spread out evenly. Same thing here. These 2 electrons and these 2 electrons have this pushing effect. And see what it does to the shape of the water molecule. So the water molecule, when you built it in lab, do you remember that it ended up having kind of a bend? And that's why. It's because those non-bonding electrons don't allow it to spread exactly out. So I'll quit there because it's 1/4 of. But what we are going to do next time is we will just finish this. So we really just got to talk about like what the shapes mean and how you can kind of think of them. If you have lab, we're actually going to do this tonight. So we'll look at the different shapes. We will talk about this and polarity, what it actually means to molecule interaction, finishing up the chapter with that. So we'll definitely be able to finish this chapter next